I'm going to demonstrate the phenomenon of beats. Beats are what happen when two sinusoidal waves of slightly different pitch or different frequency overlap with each other. We'll hear it in this example. What you're going to hear are two separate pitches, which are very close to middle C in pitch and frequency. When you hear them separately, they sound virtually the same. But when they overlap with each other, you will hear a fluctuation, a wobbling of the sound that occurs that lets you know that, in fact, they're not exactly the same pitch. If you wore headphones during that demo, one of the pitches came in the left ear, the other one came in the right ear. The sound waves, in fact, weren't directly overlapping each other. However, in your brain, there must be electrical signals which overlapped to produce the beating effect. So, why does this happen? Anytime two sinusoidal waves of slightly different pitch are superimposed on each other, you'll get a beat effect. Let's see why it happens. At this moment, this is a snapshot of these two sinusoidal waves. At this moment right here, this time, it's trough upon trough, and you get a large amplitude trough of the sound waves. So at that moment, they're overlapping, and it's a loud sound, large amplitude. However, a little bit later, remember, these waves are actually moving. So a little bit later, the wave advances, say, to the left, and you're hit by this part of the waves instead. And at that moment, it's peak upon trough, the waves cancel, and you get a muted sound, no sound. They're destructively interfering at that moment. And a little while later, the waves advance to the left again, and now it's peak upon peak, and you get a loud sound. So the sound waves are periodically constructive, destructive, constructive, destructive. That's what leads to the wobbling, the fluctuation of the sound when beats occur. Beat frequency has many different applications. For tuning instruments, you have to match the pitch. But also it's used in astronomy, for example, where you're looking at like microwave signals from space. Those are gigahertz range, trillions of hertz. How are you going to tell the difference between a million and 1,000,001 hertz? Okay, the answer is you overlap the two signals, and the overlap beats at 1 hertz, which is easily measurable. Okay, so our example of a beat frequency here, we want to notice that the tension in wire B is going to be different from A. Therefore, they'll have a different fundamental frequency. So our job is just to figure out what the tension is in B and in A, figure out the fundamental frequency of both, and look at the difference to find the beat frequency. So first a sketch. Here's the bar, and I need to draw all the forces here. B is going to be slightly larger in tension because the cube is closer to the right side. So I'll have some larger tension FB, smaller tension in A. I have the cube of lead, which is 185 newtons, and that's 3/4 of the way down the bar. Now the bar itself weighs 165 newtons. That weight effectively pulls from its center of mass. So to figure out the two forces, I'll need two equations. The first equation I'll use is the torque around this point on the left side. The torque around this point has no contribution from A. FA produces no torque around that point, but the other three forces do produce a torque around this point. So the torque from B will be L times FB. L is the length of the bar. These two torques are negative. I'll have minus 3/4 L times 185 newtons, and then minus 1/2 L times 165 newtons. And that net torque has got to be 0. That lets me solve for FB. FB comes out to be about 221 newtons. Okay, to find A, I can just look at equilibrium of forces. All the forces together have to add up to 0. So in other words, A plus B together have to balance the weights minus 165, minus 185. That lets me solve for A now that I know B. So FA, it comes out to be about 129 newtons. So with that, I know the tensions in the two wires. I can now find the fundamental frequency of each one. F1 is equal to 1 over 2L times the speed of waves in each wire, which is the square root of the tension, divided by mu. The fundamental, that's why it's F1. So given the two tensions, I can plug in and figure out the two different frequencies. They come out to be about 88 and about 116 hertz. So the delta F comes out to be about 28 hertz, the difference. So when you pluck both strings, you'll hear the average of their two pitches, but you'll also hear that sound fluctuate at about 28 hertz. That's the beat frequency.